Okay, this is important. So this is exactly the first thing that you need to determine the direction of Q. Okay, now let's calculate tutorial 1.1. Rate of heat transfer on a cool day through a rectangular window that is 1.2 meter wide and 1.8 meter high has a thickness of 6.2 millimeter. A thermal conductivity of 0.27 watt per mc. The temperature inside the house is 21 degrees C and the temperature outside the house is -4 degrees C. Okay, let's try to solve this problem. First, what we need to do is we draw the diagram. So this is to represent the wall. Okay, this is inside and outside. The temperature of inside wall is represented by T1 and the temperature for outside wall is T2. Okay, next we need to draw the Q direction, heat transfer direction. So since T1 is 21 degrees C and T2 is -4 degrees C, so the direction of Q is from left to right. Okay, this is important. So this is exactly the first thing that you need to determine the direction of Q. Okay, so we have the value of K, W, and H, as well as the thickness of the wall. Okay, so we have all the information. Okay, now we can calculate the rate of heat transfer. Okay, we're gonna use the Fourier's law of equation. Q equals to negative Ka dt over dx. Okay, so from there equals to negative Ka T2 minus T1 divided by small t. Okay, which is the thickness of the wall. Okay, since we know T1 is larger than T2, so we can arrange this equation in order for us to get the positive value of heat transfer, Q. Okay, so the surface area is H multiplied with W, which is the area perpendicular to the direction of Q. Okay, so we fill in all the informations, the values. So finally what we got is Q equals to 2352 watt. Okay, so that's how we calculate conduction through a wall, heat transfer of conduction. Okay, notice I use T as the thickness, small t, but most of the time it depends on you how you want to represent the thickness symbol. You can use L as well for the thickness. It is up to you, but the thing is you need to ensure that you know which one is the height, which one is the width, and the thickness of the wall. Okay, so this problem is during winter, so that's why the outside temperature is -4 degrees C, which is really cool in comparison with the inside temperature. Okay, the other thing is if you notice, the statement is temperature inside the house and temperature outside the house. Okay, because there are no other information given, so we assume that the temperature of the room area for inside the house is similar to the wall temperature. So the same concept we apply to the outside as well. Okay, now we proceed with second tutorial. Atmospheric air at a temperature of 10 degrees C flows with a velocity of 5 meters per second across a tube with an outer diameter of 1 centimeter and a length of 5 meters. The surface is maintained at 110 degrees C. Okay, so we need to determine the rate of heat flow from the tube surface to the atmospheric air if H is equals to 85 watt per m squared C. Okay, before this we have conduction. Okay, so basically in order for us to determine whether our problem is conduction or convection, is one is the value given. Okay, this is the easiest way. If the value given is K, that is thermal conductivity, so meaning our problem is conduction. Okay, so for our case here is H, which is the convection coefficient. Okay, next is you can also determine based on the definition of conduction and convection. For this case is clearly convection because involved of air movement. The fluid is in motion, so our case is going to be convection. Okay, so let's solve this problem. So I'm going to change the summation of the temperature. Instead of TW, I'm going to use TS, which represents surface temperature. Okay, next is surface area. Okay, this is the surface area. So how basically we determine the surface area is based on the area that exposed to the air movement. I mean fluid movement. Okay, so the area is by the L. The diameter of the cylinder is 1 centimeter, so therefore the value is 0.01, and the length of the pipe is 5 meter. So therefore your surface area you're gonna get is 0.157 meters squared. Okay, so we're gonna use Q equals to HA Ts minus T infinity. Okay, notice here we have V equals to 5 meter per second. That shows that air is in motion, the velocity of air. But please notice we're not going to use this V in our calculation for heat transfer, right? But the value should be there to show that this problem is actually convection. Okay, so let's continue our calculation. Okay, so fill in all the values, pH, temperatures, and the area. So finally what we're gonna get is Q equals to 1335 watt. Okay, so we continue with tutorial 1.3. A horizontal pipe with a 50 mm outside diameter is maintained at a temperature of 50 degrees C in a large room where the air and wall temperature are kept at 20 degrees C. The surface emissivity of the steel pipe may be taken as 0.8. Okay, so we need to calculate the heat loss by radiation per unit length. So again, I'm going to change the summation of temperature. T1 becomes Ts, surface temperature, and the ambient temperature is T infinity. Okay, for radiation, you need to ensure that you need to change the temperature. Instead of degree C, you need to change them into Kelvin. So now your surface temperature becomes 323 Kelvin, and the ambient temperature becomes 293 Kelvin. Okay, the surface area is the area of surface that exposed to the ambient. Okay, so our surface area is pi dl. So since we don't know the value of L, so we're gonna get is 0.157 L. Okay, so take a look what they want. So what they want is heat loss by radiation per unit length. So Q divided by L. So our equation become Q divided by L equals to emissivity multiplied with sigma pi d, and then Ts to the power of 4 minus T infinity to the power of 4. So we're going to substitute all the value. Emissivity is 0.8 and the sigma is 5.67 times 10 to the power of negative 8. Pi d is 0.157, and then the temperatures. Okay, why we need to change the temperature into Kelvin? Because we have 2 to the power of 4 here in our equation. Compared to the convection and conduction, you only have a temperature surface minus temperature infinity. So if you use Kelvin, the value is going to be the same even when we use degree C as well. Okay, so finally what we're going to get is heat loss by radiation per unit length is 25.03 watt per meter. Alright then, so I've shown you all three modes of heat transfer and how we can calculate the heat transfer as well for each mode.